So I want to introduce myself. Again, I'm Brian Campbell. I've done a lot of different things in the industry, and I think Nishant, who works at Identropy, maybe described me best when he tweeted this out for his 10,000 tweet earlier this year. He did the Venn of Identirati and tried to categorize a lot of where various people fell in this. And right over here on the right, I think I've occupied the most coveted position on the entire Venn, which is nobody really seems to know what I do. And I'm not always sure what I do either. But I do spend a lot of time working with standards and helping to develop some of the identity internet standards that we work with. And so that's primarily going to be the focus of what I'm talking about today. Another piece of my introduction here is Ashish, again, caught me, I think, 2 years ago, running around. I like to take photographs. You'll probably see me with a camera a lot here, photographing various pieces of the lifestyle here. And so he caught me there in the middle of the keynote down on the floor taking a picture of Gunnar Peterson. The actual photograph up here, Identity is up on the right. So not only do I like to do that around the conferences here, but I also like to sort of self-promote myself by tying photographs into the presentation. So you've been warned. So I'm going to give a quick sort of intro overview of JWT, or JWT, sorry, I'm going to say both interchangeably, and Jose. So Jose is the JavaScript object signing and encryption specification suite. Jose for short. The IETF, where this was developed, really likes to have sort of cutesy acronyms for their standards, and Jose is one of those. But they do, it's nice, it sort of rolls off the tongue, and it enables a lot of great jokes like my t-shirt. One of the pieces of Jose is the JSON Web Signature suite. It's a way of representing content secured with a digital signature or message authentication code using JSON data structures and base64 URL encoding. JSON Web Encryption is just like JWS, but it's designed for encrypting content. JSON Web Key is a way of representing cryptographic keys using JSON. And then JSON Web Algorithms actually isn't itself its own specification, but it's sort of a separate standard that defines the actual cryptographic algorithms and identifiers used in the previous three. It's meant to be a way of sort of enabling more cryptographic agility within the previous three specifications. So the previous three sort of define the structure and content of the messages or the tokens, while the algorithms independently define the algorithms that are used underneath, hopefully enabling them to be updated over time as new and stronger algorithms appear without affecting the base specifications. And then building on top of all that is JSON Web Token. It's a compact URL-safe means of representing claims or attributes, depending on how you like to refer to them, to be transferred between two parties. And a JWT, or JWT, is really nothing more than a JWS and or a JWE with JSON claims as the payload. So a JWE and a JWS can encrypt or integrity protect arbitrary content. But a JWT itself defines what that content is and defines it as a set of claims or attributes about a specific party encoded in JSON as the payload of one of the other objects. And they can actually be nested inside of one another as well. So these two things are already out in the wild. They're not even official standards or RFCs yet, but they're pretty well regarded. They recently won an award over at the European Identity Conference. I'll let you read the caption. And they're widely used already, even though they're not full standards yet. They're deployed throughout OAuth. JWT is being developed in the OAuth working group and is a common token format for an OAuth access token. JWT is widely used in OpenID Connect. It's the format of the ID token, which is effectively the assertion, the SAML assertion of the newer OpenID Connect standard. Mozilla Persona uses them, but not sure about the future of that particular standard. It's still going, but a little hurting right now. The W3C Web Cryptography API makes a lot of use of the JSON Web Key specification, building out some cryptographic APIs for use in web browsers. And they're used in a lot of other places as well. I've found them used personally in my own development. They're just a very nice tool to apply to a variety of problems of basically data exchange, particularly about identity between different parties and being able to protect that and exchange it in a secure and efficient manner. Some people because of the JWE, JWS, JWA, JWT, have come to sometimes seriously, sometimes a little bit humorously, refer to these as the JW star specification. Pat Patterson a while back tweeted, JW star, the WS star of the new millennium. Drew up a little diagram of them here. So I asked, what's in a name? It's kind of funny. It's a name that people are maybe familiar for. But you wouldn't name your child Attila the Hun, would you? WS star has some pretty negative connotations to a lot of us in the industry and people that have been around a while. And so even though the standards break out and there's a lot of different standards and they kind of nicely compose into the JWX, JW star group, I'm asking politely that we don't call it JW star because it carries so many negative connotations sort of related to the prior work that came before with the WS star specifications, which have been useful in their own right, but maybe quite a bit more complicated and difficult to work with than most people would have wanted. And I say, I didn't name my kid Attila the Hun either, but sometimes the way he acts, I think maybe he did. So, what would Jose do? This is the first time I've ever been able to wear a t-shirt that corresponds with the slides I'm putting up here, but I think Jose would call it JW steak. It fits the acronym nicely, it rolls off the tongue. Admittedly, I've been pushing this for about a year, and even I haven't really gotten any traction on it, but I still like it. And really, because who doesn't like a good steak? Okay, fine. Technically speaking, my vegan coworker does not like steak, even if it's good. But really, let's not split hairs on this one. So that was sort of my introduction, and I don't know how to transition into the sort of more technical details here. So it seems easier to come out and sort of say it. This is my awkward transition. Paul Madsen here eating a Slim Jim, wearing a sailor's outfit with a bow tie. Doesn't get much more awkward than that. Hopefully this takes a little bit of the awkwardness away from my transition here. But I'm going to jump into a little bit more of the technical details of some of these standards, hopefully giving you some more information about just understanding how they work and enabling you to work with them more effectively. So the first thing here is XML seems to be the thing of the past, and all the cool kids are doing it. JSON, lightweight and human readable data interchange format. I'm not going to go into a lot of detail on it, but it's sort of developers and deployers are voting with their feet. This seems to be the accepted de facto standard for data interchange now, both in application development and standards development. This is what people are using. One common thing that comes up is encoding. SAML and some prior specifications made a lot of use of base64 encoding, which is really just a means of encoding arbitrary binary data into printable ASCII format. It's an algorithm that takes every 6 bits and converts them through a lookup table into one character. And those characters come from a 64-character alphabet. It's the 62 alphanumeric characters and a plus and a slash. And then at the end, there's some padding. And what you end up with is every 3 bytes of binary data ends up as 4 characters encoded. And this allows you to transfer binary data in sort of a clean, clear, printable, sort of text-armored format. That's been in use quite a bit. And even though it was developed around the same time, actually in the same specification, there's another variant of base64 encoding. It's base64 URL encoding. And it's just like base64, but it uses a URL-safe alphabet rather than what's almost a URL-safe alphabet in regular base64. And so you see that they use a dash and a plus rather than the, wow. I got my characters wrong here anyway, sorry. Rather than the underscore and the slash, that should be a little bit different. And the padding is typically omitted. My apologies. Basically, they replace the 2 characters that would normally need to be URL encoded with 2 that don't. And you end up with the ability to encode something. The example shown here, so I took 32 random bytes and encoded them. On the top is regular base64 encoding. On the bottom is base64 URL encoding. They look very similar, except for a few cases where you can see like the plus here is a dash, plus dash, / and underscore, and then the padding is omitted on the same. They look largely the same, However, the key difference comes when those tokens are URL encoded, which are completely cut off here. The slides seem to have taken it. But I apologize for that. The key being that the top one is the URL encoded base 64, and you see that the special characters are % encoded, which expands the token and basically changes its format, while this one, even going through URL encoding once, twice, or 3 times remains the same. So there's a couple, but there's one remaining unreserved URI character, a character that doesn't need to be escaped in or encoded in URLs, and that's the period. And this will prove important in a little bit. So I want to take a little bit closer look at Jose, starting with JWS. JWS is short for JSON Web Signature. It's a way of representing content secured with a digital signature or MAC, a message authentication code. It uses JSON data structures and base 64 URL encoding. Encoded segments are concatenated together with that remaining unreserved character, the dot. These are basically intended for space-constrained environments, typically HTTP headers, authorization headers, or URI query parameters. And it's conceptually really simple. It's a header, dot, payload, dot, signature, where each of those different pieces are base 64 URL encoded. And that comprises the entire JWS token. The header itself is a little bit of JSON that describes exactly the operations applied to it, whether it was a signature or a MAC algorithm. There's a number of reserved headers, so it's just JSON name value pairs, and there's reserved header names that are used commonly and defined in the specification. And one of them is the alg parameters, and this stands for algorithm. The header names are typically short, 3-letter is the convention, trying to keep the whole size of the token under control. It's sort of a small step, but using short identifiers and names for claim or header values is one thing they do. So alg is short for algorithm. And so it can represent either an HMAC, an RSA PSS, or an EC elliptic curve digital signature algorithm. There's also a none signature algorithm, which is, there's been some controversy around it. It's sort of equivalent of a null cipher suite, but it's there, and in some cases will be useful. It's also extensible, so there's a bunch of algorithms defined to be used and should be interoperable, but in the future, new algorithms are being developed. They can be applied here without updating the base specifications. There's a KID header, which is short for key ID. It's a way to help identify which key to use. So when a producer of a JWS signs it, he can give a little hint via key ID to the consumer about which key was actually used. And there's a bunch of other stuff that help identify keys. You can point to a set of keys online, to tokens, not tokens, certificates. You can include certificates in line or refer back to certificates or keep them directly inside the header themselves. There's also a type and content type, which are sort of not particularly well-defined headers, but are intended to allow the consumer some hints about what the actual thing is. Content type actually is pretty helpful. It can be sort of similar to a MIME media type that describes the actual payload of the JWS. The type header itself is something I haven't quite found a good use for. It just says what this thing is, and you kind of already know what the thing is. So one example, kind of going English to JSON here, would be an example header where you might say, I signed this thing, whatever it is, and I used RSA with SHA-256, and I signed it using a key we both know as Niner, which would be the key ID, and you can find that corresponding public key at this particular endpoint. And then, so taking that text and sort of translate it into the JSON header, you see alg RS-256, which is what I signed it with, KID Niner, and then JKU is the JSON web key URL at this particular endpoint. So that gives the receiver of this a lot of hints about how to verify it. It says how it was signed, it says what key it was signed with, and it says where you can find the corresponding group of public keys from which to select that particular key. So there's a number of sort of predefined algorithms in JWA for JWS. basically there's 3 different strengths of each one. There's HMAC using SHA, so that's HMAC, a hash meshes authentication code. It's sort of like a symmetric digital signature, pre-shared secret, and then that secret's used to calculate a digest, a secure digest over it. They come in different, there's 3 different strengths that can be used, SHA-256, HMAC SHA-384, and HMAC SHA-512. Then there's also RSA digital signatures, also using SHA-2 in the same strengths. There's elliptic curve digital signatures, also with SHA-2. And there's 3 different elliptic curves defined for usage here, along with the various strength SHA algorithms. And there's also define the RSA provably secure, the PSS algorithms, I can never remember what it stands for, which are not nearly as widely used or deployed as the RSA PKCS 1.5 digital signatures, but are at least in theory more secure. Some people felt it was important then to include them in the set of standards. Although really, I think as time progresses, people will probably move from normal RSA to elliptic curve signatures, and the PSS stuff I think will maybe not gain as much adoption. And like I said before, there's this unsigned plain text, which is defined by the alg parameter or alg value of none. And it's just a way to basically use the same encoding and sort of structure of the token, but do so without actually applying any cryptographic protections for it. So you need to be careful with it, but it's sometimes useful to have the same encoding. I'm going to get into a couple of quick examples here, but I wanted to provide a little bit of context for the sort of semi-humorous jokes I'm going to put into there. At Ping Identity, we have a lot of different offices, but 2 of our main engineering groups are in America and in Canada, and we like to have a friendly rivalry between the 2, sort of, as is the case for countries that are really so much alike. But there's occasionally some jokes that fly back and forth. So I'm going to start with sort of a jingoistic JWS example. I want the payload of my JWS to be USA #1 because I'm from the USA and we are #1. And I want everybody in our Canadian offices to know that. And I want this not to be tampered with. I don't want somebody to come in and change the content of this and misrepresent me as a Canada lover. So I'm going to sign this payload. So going through the JWS work, the first thing we do is encode the payload. So you take the payload and you take the UTF representation of that and base64 URL encoded. And that's what you see there in the sort of opaque looking characters. The next thing you do is produce the header. And so I've decided I'm going to sign this payload with an elliptic curve algorithm using the P256 curve and SHA-256. I'm going to sign it with a key that we collectively know is my first key. And so you get alg, ES256, and KID, my first key. I take that whole header and similarly base64 URL encoded. So we have 2 pieces there, the encoded header and the encoded payload. Those are concatenated together with a period to produce the secured input. And the secured input is basically what the signature is calculated over. So that whole piece is fed into the signature algorithm with the private key of the key that I'm using, and that produces that is the secured input, excuse me. And that produces the actual signature value, which itself is binary. And so we base64 URL encode that as well. That's this value here. And finally, the JWS, and it's called the compact serialization, is produced by taking the secured input, which is the header encoded, period, the payload encoded, period, the signature encoded. And so you can sort of think of that as this, even though you see it encoded there. You have your header in JSON, dot your payload, what you're actually signing, dot the actual signature value. And that's sort of step-by-step way of showing how you can produce an actual compact serialized JWS. So going on a little bit further, I want to jump in and look at JWE. JWE stands for JSON Web Encryption. It's very similar in motivation and design to JWS, but it's for encrypted content, so it's meant to be relatively compact. It's meant to be URL safe. All the same sort of design principles come in, but for encrypting content rather than applying a signature to it. It's a little bit more complicated. There's the same reserved headers in general, plus a few bit more. There's the algorithm header, And the alg header for JWE defines or describes the key management or key wrap or key agreement algorithm that's used here. So it explains how the two parties are going to agree on the symmetric key that's used for actual content encryption. I'll talk a little bit about that more in the next slide or two. And then there's a new header, ENC, the encryption method. This is the actual symmetric encryption method that was applied to the content based on the agreed upon key figured out or derived from the alg parameter. And there's also a zip algorithm, so you can compress the content during the encryption process to try to make it a little bit smaller. And then there's all the other ones I talked about before, the KID and the key ID, which is useful, really useful for identifying the key, and then a variety of other ways, because no one can kind of agree on one, to identify the keys used in the process. As opposed to the 3 parts of a JWS, there's 5 parts to a JWE. It starts with a header, which is the same thing as the JWS header. It's just the JSON header with the various pieces, base64 URL encoded. And it's dot concatenated with the encrypted key. So in not all, but in a number of the key agreement algorithms, there's an encrypted key that's passed along in the message. There's an initialization vector, which is the next piece, which is just used to feed into and add entropy to the symmetric encryption algorithm. There's the actual ciphertext is the next component. So this is the encrypted payload. And then finally, at the end, there's an authentication tag. And the authentication tag is a way of applying an additional integrity check on top of the symmetric encryption algorithm, which prevents a number of sort of problematic attacks that have occurred on unauthenticated encryption. So there's 2 kind of basic types of symmetric encryption. There's authenticated and unauthenticated. And authenticated is basically just an additional integrity check on the ciphertext that allows someone the receiver of the message to know that the ciphertext has been altered before they try to decrypt it and then stop the process. And that prevents a number of sort of chosen ciphertext attacks that people have more recently developed that allow people to more efficiently get at the bottom of the keys. So or extract keys from systems. So the entire JWE set describes only authenticated encryption algorithms, so as to sort of put behind us any of the potential problems with unauthenticated encryption. So there's sort of 2 main classes of encryption algorithm for the actual content encryption. What encryption is applied to the payload itself with the agreed upon key. The first one is authenticated encryption with advanced encryption standards, encryption standard AES in GCM mode, which is an AES algorithm mode that incorporates authenticated encryption directly into it. And there's 3 different strengths of that with different key strengths. And there's also an authenticated encryption with AES CBC and an HMAC SHA-2 composite. So AES CBC is widely available. It's available on almost every platform, but itself is not authenticated. It doesn't include that authentication tag. And so what Jose has done with JWE is define this sort of composite algorithm that gives you authenticated encryption-like capabilities using lower level constructs of AES CBC and HMAC SHA to put them together and provide authenticated encryption-like protections while only using the sort of lower level non-authenticated encryption pieces, but which are widely available. So a lot of platforms don't have the AES GCM, and some of this work here in Jose by providing these composite algorithms brings a lot of the value of those into systems that might not necessarily have support for the newer algorithms. The content encryption is actually kind of the easy part. Once you have a key and you symmetrically encrypt the content with it. The harder part is agreeing on the key that's going to be used for content encryption. And there's a lot of different ways to do this. Looks like a little bit got cut off. But the first one is direct encryption with a shared symmetric key. So we might have exchanged keys previously, and this is a way to just say, go ahead and use that key directly as the encryption key. There's no other step here. And the algorithm parameter for that is dir, again, trying to keep things short. But this is one case where you won't actually see that second component, the encrypted key part of the compact serialization. There won't be an encoded encrypted key there. It'll just be 2 dots, and that field will be blank. There's RSA 1.5, which is, this does encrypt the key. So the public RSA key, if I'm encrypting to you, I take your public key, I generate a random content encryption key, and I encrypt that with your RSA key, so only you can decrypt the encrypted key and then use that for content encryption or decryption. Similarly with OAAP, so optimal asymmetric encryption padding is a newer RSA algorithm that's provably more secure than the other one. The Jose suites support both with the goal of sort of providing functionality that's commonly available on all platforms, but also supporting and encouraging the use of newer, stronger algorithms. There's AES key wrap, which is a way of using a pre-shared secret to encrypt the key that's actually used for content encryption of this message. So it's sort of a two-phase symmetric encryption step where we have a shared secret, but for the actual message itself, I encrypt it with a random key and use the key that we both knew to encrypt that key itself. Sort of protects the core key from some cryptanalysis type things by removing it one step from encrypting the actual content. There's the same thing with AES GCM key encryption. So there's a way to use the GCM algorithms to do key wrapping with AES. And there's a whole suite of elliptic curve, Diffie-Hellman ephemeral static key agreement using concat KDF. So using elliptic keys, rather than generating a random key and encrypting it to send to your partner, there's a key agreement that's used by generating, when I'm sending a message to you, I generate an ephemeral EC key set and do a Diffie-Hellman key negotiation or key agreement and use that, the result of that, as the encryption key, the content encryption key. And then there's a key derivation function algorithm there to allow whatever that agreed upon key is to be stretched or shortened to the appropriate length so we both have the same thing. And then you can also use that same algorithm, agree on a key using Diffie-Hellman, and then rather than using that key directly, you can use it as an AES wrap key to wrap a randomly generated symmetric key. There's a lot of different options here. And finally, there's a password-based encryption standard using HMAC SHA-2 and AES key wrapping. And this isn't really for exchange of tokens between parties the way that we typically think about them as an ID token or an assertion or something like this. But it's a way to do password-based encryption, which is often more suitable for maybe storage, local storage of something local on a file system. It shouldn't be something that's used to transmit things over the wire, but it's a way to strengthen the password into an AES key and use that as the actual content encryption key. So back to my examples. I'm going to go with kind of a confessional example of JWT. So the truth is I actually really like Canada. You look at this beautiful place, how could you not like it? But I don't want everybody in the office to actually know that. So I want to be a little bit careful. I want to say this, but I'm going to encrypt it so not everybody can know. So to produce the JWT, I first need to get my header. Here, the key that I'm going to use, I'm going to say use this one, And I'm going to encrypt this using RSA OAP, and I'm going to encrypt the shared key with OAP, and I'm going to encrypt the content with that composite AES HMAC algorithm I was talking about before. I take that, I base64 URL encode the header. I randomly produce a 128-bit initialization vector and base64 URL encode that. I take a 256-bit random key, and it's kind of an interesting piece. The composite algorithm itself takes a composite key. So even though I'm using an AES 120-bit AES algorithm, I'm actually needing to produce sort of a composite key for two things. So I'm actually using a 256-bit key where the first half will be used for encryption and the second half will be used for the authentication tag calculation of the message. So I take that 256-bit random key, encrypt it to the recipient using RSA OEP, and then base64 URL encode all that. You can see this is probably the largest part of the whole message, largely from the size of the RSA algorithm output. I take that key and apply the encryption algorithm to the payload. So I take the payload, I actually really like Canada, take the random key and AES CBC encrypt that, take the encrypted content and base64 URL encode that, which you see here is the relatively small piece of the output. And finally, I take a left truncated SHA-2 256 HMAC of the encoded header, the initialization vector, and the ciphertext all together as the input into that HMAC and produce the authentication output tag using SHA-2 256, truncated in half so it's a little bit smaller. And that's that value there on the right. And finally, I produce the full JWE by taking each of these encoded pieces, putting them together, concatenating them together with a dot. So it's the header dot encrypted key dot initialization vector dot ciphertext dot authentication tag. And you get the final result here on the bottom. And it's you can see it's still relatively small. It's not as compact as the JWS, just by virtue of some of the algorithms employed here and the need for a few more pieces for encryption. But relative to some other things we've seen historically with encryption, it is relatively concise and terse. Sorry, I'm a little flustered, kind of tired. I try to make some humor here, though. And when I was putting together those examples, going with sort of the Canadian-USA comparison there, I went to Google, just looking for some insight and some fun, and I started to Google, never trust a Canadian. I'll remind you that my name is Brian Campbell. And as I was typing this, and Google's lovely little Ajax type ahead functionality comes out, this is what I got. Apparently, there's some history with my name. So I gave that up and went with just the two simplistic examples I had before. So real quickly, then, I want to turn to JWT or JWT. This is JSON Web Token. It says right there in the standard that the suggested pronunciation of this is JWT. Some people do this, some people don't. I find myself wavering back and forth. Sometimes I'll say JWT, sometimes I'll say JWT. I don't really know if this is going to catch on or not, but it feels worth mentioning. They are the same thing. JWT and JWT are the same thing, and some people say it differently, some people say both. It itself is a compact, URL-safe means of representing claims to be transferred between two parties. I think I saw that text directly from the specification. But really, it's an assertion. It's like a SAML assertion using some different technology to encode it. It's a way for one party to transfer secure claims to another party. It itself is a JWS and or a JWE with JSON claims as the payload. So I talked about this a little bit in the beginning, but a JWT itself isn't a whole lot more than a JWS or a JWE, the technology that I just discussed. The main thing about it is that the payload of that actual message is a set of JSON claims. And a JW claim itself is a piece of information asserted about the subject, or in some cases about the JWT itself. And claims are represented as name-value pairs, and basically consisting of a claim name, whatever the name of the claim is, and a claim value, which can be any JSON object. So you can have a claim name that has a complex JSON structure as its value. It's legal, it can happen, but in most cases, it's just name-value pairs, a name and a value encoded in JSON. There are some reserved JWT JWT claim names. These are just ones that have been defined in the standard and should have common semantic meaning to everybody in all implementations. So there's ISS, which is the issuer. This says who issued the token, who created this particular token. There's the subject, who's the token about. Going back again, these are all generally three-letter names to sort of keep the token short. There's audience, who's the token for, who's the intended recipient of this token. There's an EXP, an expiration time, when does the token expire. There's an NBF, which is not before. It's when does the token become valid? It can't be used prior to this. There's an issued at, IAT, when was the token actually issued? And there's a JTI, which is a unique identifier for the token itself. In the JWT specification themselves, all of these things are optional. There's no sort of profile of what's needed or what not. It's up to the actual application or context of use to define what's needed. But these are, in the JWT specification, they're sort of just ways to provide commonality and standardization around the name and the meaning of it. So a little bit of look at a JWT itself. This is a JWT encoded. Did a little bit of color encoding here. The red there is the encoded header. The black is the encoded payload, and at the end is the encoded signature. So the header unencoded is pretty simple. It's just saying this is it's a JWS. We know that for a couple of reasons. One is that it has 3 parts. The other then is that the algorithm refers to a signature algorithm rather than a key negotiation algorithm. It's saying that this JWT was signed with a 256-bit elliptic curve signature algorithm, actually a 256-bit curve with the elliptical signature applied to it in SHA-256. And it's also saying that the key I use for that is something we collectively know by the ID of 5. There's no semantic meaning behind the kit. It's just a way it's an ID to be able to refer to or reference keys. The signature is just a bunch of binary data encoded. It's just a signature encoded that way. And then the payload's kind of the interesting part. So unencoded, it's a bunch of JSON. It's saying that idp.example.com is who issued this. It's saying that it expires at this particular time. Times in JWT are represented as the number of seconds from the epoch, which is a nice, compact, and easily usable time representation. It's not particularly human readable. I have no idea what that is, other than it's probably maybe a year ago when I first started working on this example. I've used it a few times. But to machines, that's really easy, and it's very error-free. The audience is saying who's allowed to use this token. If it's going to somebody else, they should discard it. This sort of defines the valid audiences for whom this token is intended. And it's just saying here that it's to be sent to sp.example.org. The JTI is just a random value that's meant to uniquely identify the token. ACR is actually something that comes from OpenID Connect, and it's the authentication context class reference, similar to the authentication context from SAML. This is just basically saying this is an LOA2 token. Now, similar to SAML, these are just sort of URI or string references that are not necessarily meaningful in all contexts, but is a way to convey the strength of the authentication event between the two parties. And this is one way to show that even though this wasn't one of the reserved or predefined header values or claim values in the JWT specification itself, it's something that's defined at another layer up and shows how these claim names can be reused and even profiled at higher layers. And then finally, the subject is me. The subject is Brian. And that's it. That's the payload of the token. It's a way of basically conveying information about me between these two parties in a constrained way that's only valid for this amount of time, signed with a key so it can't be tampered with. So the size is one important aspect and sort of benefit of JWT. And just to give you an example here, compare basically, it's not 100% the same because there's a few minor semantic differences. But for the most part, these are two equivalent tokens. They say the same thing about the subject. They're signed with the same key. They have the same claim or attribute information. They have the same issuer and audience information. And on the top, you can see that whole thing is represented in a JWT in a couple of lines. Where the bottom, the SAML assertion is rather more verbose. So you can see some benefits there. And interestingly enough, the JWT itself, because of the use of the base64 URL encoding and the period concatenation, it's already URL safe for transmission via query parameters, although you shouldn't do that, maybe a form auto post or an authorization header. Whereas the SAML assertion isn't safe to transfer that way. So in order to transfer it using sort of standard web technologies that we're used to, it would need additional encoding on top of it, which would make it even larger. But size is valuable in sort of the benefits of the JWT, but there's a lot more value too in sort of the bare simplicity of JWT versus things like XML digital signatures and SAML. So generally, simpler is better. It means less interoperability problems. Generally, simple is better for security. So the web-safe encoding with no canonicalization is a huge benefit of JWS and JWT over XML DSIG and SAML. So canonicalization is the process that occurs in XML digital signatures to basically try and take an XML document and normalize it so that the same document that might have the same semantic meaning but have different actual markup based on namespaces or white space or all kinds of different things, a way to sort of normalize it into one thing and use that as the input into the signature calculation. And it's a very complicated process. It's sort of nice in theory, but it often doesn't work very well. And one of the design decisions made in JWS was to skip the canonicalization step entirely, not make an attempt to produce or define canonical JSON representation, but just sort of sidestep it completely. And in a way, base64 URL encoding is used as sort of what I think of as a poor man's canonicalization. So rather than trying to canonicalize the content itself, we just encode the whole thing and transfer that so it's not subject to any sort of changes on the wire or whatever, and produce the signature over that content. So we're not trying to canonicalize the JSON or any of the actual payload itself, but simply produce a sort of repeatable, reliable encoding of that in the base64 URL encoding and skip the canonicalization step entirely. As a result of the simplicity, hopefully we get improved interoperability and better security. So oftentimes the result of complex systems is security problems. Security often arises at the behest of complexity. The improved interoperability, I think, so far has been generally true, although I was looking at a support case last night where we had some problems verifying a JWS signature. So it's not all rainbows and unicorns, but I think generally it's been true. The thing about not having canonicalization is, because it's simpler, it's not just a little bit better. The fact that there's not that step in there eliminates entire classes of very serious attacks. So XML digital signatures have been plagued over the years with really clever and intelligent researchers coming up with really crazy and very serious attacks on the system. So this is Brad Hill, who actually, this is him speaking at CIS a few years ago. And he's not all of these, but he's researched and published a number of these attacks. And almost all of them involve attacks on the actual canonicalization step itself. So you're taking this data and transforming it in sort of ways that are described by the data itself, and it opens the system up to a number of very, very serious problems. You can read them yourself here, but the nice thing about JWS is it doesn't just sort of go in and try to Band-Aid fix these previous problems that we've seen in another similar standard. It took an entirely different approach to the whole thing and did it in a way that these sorts of attacks don't even come into play. Talk a little bit about JSON Web Key, or JWK. It's a JSON data structure that represents cryptographic keys. You can represent public-private keys this way. Define their RSA and elliptic curve keys. Notably, DSA is not there, although one could profile it if they need it. I think it's sort of a nod to the fact that DSA keys are sort of falling by the wayside. You can also represent symmetric keys this way. It's called an octet sequence, JWK. It's not something you want to publish, but it's very useful to be able to represent keys in a common format, whether they be public, private, or symmetric. JWK is really interesting. It can be included directly in a header of a JWS, E, or T. It can be published at an HTTPS endpoint and referenced in a message. Thank you. It can be used in place of self-signed certificates. Oftentimes, self-signed certificates are used as a way to send around public keys just because it's a common and easily, and there's a lot of tooling for parsing and dealing with certificates. But a lot of times they're just used as sort of an empty wrapper around the key itself, and all the actual certificate metadata is unimportant. You can save them in a file. You can send them an email. There's a lot of different things you can do with them. So to give an example of what I mentioned before about referencing in a header and pointing to an endpoint, say you have this is actually the JWT from earlier. We have, it's been signed with an elliptic curve key, and we're saying it was signed with a KID 5. And over somewhere else, probably published in an HTTPS endpoint, meaning that consumers of this key set can go to a secured endpoint, authenticate the host, and have some assurance that these are actually his keys, can go and look up the key set online. Here's a JWK key set. It's a list of 3 elliptic curve keys, each identified by a different KID, and he can use the KID in the header to make the association of which of those keys was actually used to sign the document and use that to verify the signature. And this gives a really nice facility to do sort of automated no-touch key rolling. So without having to have people on either end of the system sort of on the phone saying, okay, you ready to roll the key? Okay, go. It can all happen in an automated fashion. The key set can over time add new keys, remove old ones, and then all that needs to happen is signal to the receiver using the KID which key was actually used to do the signing. So I think I'm going to run out of time here, but I did want to say that the relative simplicity of JW Stake, let's all keep saying it, it's nice for all the reasons I mentioned before, but it's also nice because it implies a simple programming interface. There's already numerous implementations out there in almost any platform or language you can imagine. And I wanted to take a quick look at one of them. I'm not going to go into a lot of the details, but I wanted to introduce Jose for J. This is an open source Java implementation of the Jose specification suite. There's a URL there. This is something I've been working on for a while. It relies solely on the Java cryptography architecture APIs for cryptography. It doesn't have any other dependencies on crypto. It has 100% algorithm support of all the Jose algorithms. It's production ready. It's used throughout Ping Identity's products already. It's what I call the referenceable implementation. There is no real reference implementation, but there's some work developing a Jose cookbook, which is like a list of Jose examples to be used to help implementers. And I use my implementation to help debug the cookbook itself, so it's relatively strong in that sense. And it is completely free of NSA backdoors. Although, if there's anybody out there, I am open to sponsorship opportunities. I'm going to skip this right now. These slides, I'll post them. They'll also be available, I hope, through the CIS site at some point. But here's a few code examples, just to give you an idea of how relatively easy it is to use. This is the actual code that was used to produce the JWS example used earlier, just a few lines here. Consuming it similarly is relatively easy. And the bulk of this code is actually the key being a string key at the top. The actual decoding and setting of the key and consuming the token itself is relatively simple. JWE is similarly a little bit more complicated, but kind of the same. This is the code that was used to produce the JWE example before. And likewise, the code to consume it. And the bulk of the value here is actually just the JWK. The RSA keys in consuming in decrypting, you need the private key, and those are kind of verbose. But once you have the key, you just take the compact serialization, throw it into an object, set the key, and pull out the payload. And it's that simple. So I know you all are probably thinking, and I am sort of too, are we finished yet? And yes, we're done. I'll see you at boot camp, maybe.